In electric vehicles, an inverter is used to convert the voltage of the high-voltage battery into three-phase alternating current. The inverter consists of 6 transistors and a capacitor. During control, the transistors work alternately to realize the AC voltage supply of the three-phase winding. The main function of the inverter is to control the speed and torque of the motor. Theoretically speaking, the motor speed can be achieved by controlling the operating frequency of the transistor. However, in practice, at low speed, it may cause the motor to generate excessive current, causing damage to the motor. Therefore, variable frequency and variable voltage inverter control is usually used. When the speed increases, the output voltage also increases linearly. The graph below shows the relationship between voltage and frequency. To control three-phase brushless DC (BLDC) motors, the 120 degrees commutation technique is commonly used. The high side device of one phase is on, the low side device of the other phase is on, and in the remaining phase, both the high side and low side devices are off at any time. In this switching scheme, each phase is connected to the power source for 120 electrical degrees. Off for 60 electrical degrees, connected to GND for 120 electrical degrees, and again off for 60 electrical degrees. It is thus called 120 degrees commutation. The figure shows the theoretical phase U and UV phase-to-phase voltage waveforms. In case of the 120 degrees commutation technique, since current flows through two resistive components at any one time, the phase voltage becomes half of voltage of power supply. In 180 degrees commutation, unlike 120 degrees commutation, each phase is commutated at any time. It means either the high side or low side device of the same phase is on at any one time. A high side device of a given phase is on for 180 electrical degrees, and then the corresponding low side device is on for the next 180 electrical degrees. This switching scheme is therefore called 180 degrees commutation. Figure shows the theoretical phase U and UV phase-to-phase voltages for 180 degrees commutation. During 180 degrees commutation, the phase voltage becomes either 1/3 E or 2/3 E. Although the above paragraphs state that a device remains on during its on period, a PWM control signal is applied to the on device in most cases. There are various control methods for applying a PWM signal. For 120 degrees commutation, either the high side or low side device is PWM controlled. There are two options for the 180 degrees commutation scheme. While either the high side or low side device is on with PWM control, one of the options keeps the other side device continuously off in this period. The other option applies an inverse value of the PWM signal to the other side device. PWM varies the width of pulses required for the switching of transistors in an inverter in order to generate an output waveform composed of many narrow pulses in each cycle. As a result, the average voltage of the modulated output pulses becomes sinusoidal. To generate a PWM signal, a signal sine wave is compared with a carrier waveform triangle. When the signal is greater than the triangle waveform, the PWM signal is high and switches on a transistor. As a result of this switching scheme, the average value of the output phase-to-phase voltages becomes sinusoidal. This way, an inverter regulates voltage.